All right, everybody. This is us starting off the rational root theorem, or also known as the rational zero theorem, depending on the textbook you're looking at. This is for us right now, at the time of recording, is lesson 18. The number for this may vary depending on the course, the year, wherever we might be. And we don't need to copy this stuff after the a sub 0, but you can press pause at any point if you want to copy this down and then listen to the explanation after. This states, if the polynomial, we're just describing the type of equation that we are applying this to. If the polynomial equation f of x is our function output equation, also known as the y equals in many equations, equals a sub n x to the n plus ellipses, plus a sub 1 x plus a sub 0, which is secretly next to an x to the 0 power, and x to the 0 power is actually equal to 1, but we don't write out the x to the 0 normally because it's times 1, so there's no point in doing that. If this polynomial equation has integer coefficients, what are integers? Integers are numbers like -2, -1, 0, 1, 2, ... in both directions. Positive, negative, whole numbers, nice, healthy numbers here. Then, and really, we could have rational numbers, but for right now, for what we're doing, we're going to focus on integers. But we could have rational, real numbers, basically, we're going to have here, okay? Then, every rational zero. Well, what are the zeros? A zero, by definition, is a number that we can fill in for x, that when we evaluate the polynomial, the answer we'll get is 0. Graphically, we know the zeros to be x-intercepts. That's not always the case because we've been introduced to imaginary numbers. And imaginary numbers do not give us an x-intercept, but they do give us 0 as an output when we fill them in. Every rational zero of the function f, or of this equation, whatever way you want to think of it, has the following form. So rational zeros will not include the imaginary zeros. These are going to be real numbers that can be written as a ratio or fraction. This is a very specific subset of zeros. They can be written in the following form: P over Q. In most books and most algebra textbooks use this format, P over Q, where P is a stand-in for a factor of the constant term a sub 0, and Q is a stand-in for any factor of the leading coefficient a sub n. A sub n is our leading coefficient. It's going to be the coefficient in front of our x to the biggest power. A sub 0 is our constant term, so it's that number all the way at the end that more than likely does not have x written next to it at all. If for some reason it does, which it probably won't, it would be an x to the 0, which is 1, right? So that's our constant term, factors of it, and then factors of the leading coefficient. If you notice, it doesn't say leading term, but leading coefficient. The coefficient is the number in front of the x, or x to a power of an entire term. It's just the number in front. Now, what the heck does this mean? Let's get into it. We can ask more questions about the format and all that during class, so I could specifically answer anything you're fuzzy on. But let's look at this in an example. Let's try it. For an example, find the rational zeros of f of x equals x to the third plus 2x squared minus 11x minus 12. Now, normally, the directions might not say find the rational zeros of something. The directions just might tell you to solve. Maybe it's a word problem and it doesn't explicitly tell you to solve, and you just need to figure out, like, okay, this is an equation. I need to set this equal to 0 for this reason or that reason. And you might have to kind of do this on your own with a lot less guidance. So if we were finding the rational zeros, finding the zeros, solving, whatever your directions might say, how could we go about doing that? Well, normally, if you had a polynomial equation and we wanted to find zeros First thing we do is we set it equal to 0. You're essentially setting the y value or the output, f of x, equal to 0. So we wouldn't see this part of it anymore, and we would have it with a 0 at the end instead. Now, we would solve, and we would try to solve the way we first learned, which was by factoring. But if we try to use factoring here, if you look, we don't have a greatest common factor, and if we try grouping, which is the next most logical thing to try, our groups will not have a matching factor. It won't work, and that's disappointing. When factoring isn't working, if it were a quadratic, well, we could use quadratic formula, and that would be great because we already have something that works. Anytime we have a polynomial basically bigger than a quadratic, and this can work on a quadratic as well, but we don't need it, we're going to use exactly what we just wrote down, the rational root or the rational zero theorem. And we're going to make a list of possible rational zeros, a short list, a finite list of possible zeros. Once we have this short list, we'll try or test them out with synthetic division until we find one that works. And what do I mean by works? I mean it will give us a remainder of 0 at the end, or in other words, it will divide evenly. And the way we make the short list is what we wrote on the previous page. What is our leading coefficient? Our leading coefficient, a sub n, is, in this example, 1. And what is our constant term? Our constant term, a sub o, is negative 12. So what's our list of possible rational zeros? I'm going to start by writing p over q equals p. P is all of the factors, one by one, of the constant term. Well, I could have positive or negative 1, positive or negative 2, positive negative 3, how about 4, and 6, and last but not least, 12. That's quite a few, but it is what it is. And what are all the factors of q, or a sub n, my leading coefficient? Well, we're lucky here. Since it's 1, we only have to worry about positive and negative 1. Now, x equals, so I'm making an actual list now of everything that is on my short list, my finite list. Well, what's 1 over 1? That's 1. 2 over 1? 3 over 1? Now you might be like, well, why are we rewriting exactly what we just wrote? It won't always match perfectly to what we just wrote, because if my leading term, say, had a 5x cubed, well, on the bottom here, for q, I'd be looking at 1 and negative 1, and then 5 and negative 5. So I would also have to take all of these numbers and put them each over 5 and negative 5 as well, which would make my list a bit longer, but it's still better than an infinite list, right? So now, what is the list of possible rational zeros or rational roots? It's this list right over here. Done. This might be the first stage of it, but the actual list comes here. So I usually write p over q myself when I make my setup, and then I write x equals when I decide each number over my options on bottom. Okay, next thing we're going to do is we're going to test using, hopefully you all remember how to use it, synthetic division. You're more than welcome to use long division if you prefer. It's just a bit long, no pun intended. And if we could do synthetic, let's just keep it moving. Little note I wrote here, when you have a quadratic factor, so once we divide using synthetic from a cubic, we're going to divide. This will be the result of a linear factor, and my quotient will give me a quadratic in this case right away. When you have a quadratic factor, the rational zero theorem or the rational root theorem is no longer necessary. Why not, you ask? Well, if it's a quadratic, maybe we can just factor it using AC method or difference of squares or something like that. Or if it's a quadratic and it's not factorable, then we can probably just use quadratic formula and be done. Put a little star here. It's helpful to brush up on the remainder theorem and the factor theorem, which are in our extended lesson for lesson 16, so you might want to take a look at that. I'll probably reference that in different examples, but let's keep going with this one on a new page here. So the p over q, and then the list of possible rational zeros I have rewritten right over here. That's what we had on the last page. Now we test these numbers. So let's say I was testing 1. When you're testing x equals 1, don't forget that that really goes with the factor x minus 1. And we're going to try and see if it gives us a remainder of 0. So I need to put my coefficients down, 1, 2, negative 11, and negative 12. I'm going to bring down that first number, 1, new coefficient times the divisor, add straight down, never been wiser. New coefficient times the divisor, add them straight down, never been wiser. New coefficient times the divisor, add straight down, negative 20. Well, that's not a remainder of 0, so it did not work. Moving on. Now we'll try negative 1. We try the easier, smaller, cuter numbers first. In 99.9% of situations, if you end up taking a calculus class and using rational root theorem, 1 or negative 1 usually works, or you'll have some other clue as to what number will work, and we'll get into that later, but you won't be sitting here testing like 45 different numbers before you hit the one that works, don't you worry. Bringing down that first number, new coefficient times the divisor, add straight down. New coefficient times the divisor, add straight down. New coefficient times the divisor, well, that's very nice. Now we got our happy remainder of 0. So what does this mean about this cubic polynomial of 4 terms? That means that f of x can factor a bit of the way into x plus 1, that came from the fact that it divided evenly by this negative 1 in the box, and then x squared plus x minus 12. Now, can we factor this on our own? X minus 1, plus 1. And then if you use AC method and grouping, which I'm not showing work for, you would get x plus 4 and x minus 3. And the directions were to find the zeros, find the rational zeros. So if I had set each of these factors equal to 0 using zero product property, what numbers would I get? I would get x equals negative 1, x equals negative 4, and x equals 3. So let's recap. Why the heck do we need this new theorem? The rational root theorem, or the rational zero theorem, is a way of organizing a finite list of possible rational roots. This does not include any irrational or imaginary roots, but it would include all the possible roots that are rational or can be written as a ratio. Once you have a finite list, and since other factoring methods didn't work, if we can try to find something that divides evenly and get our polynomial down to at least the quadratic, or at least something factorable by grouping or some other method, then we could continue and fully solve that equation. Let's look at another example. Find all the real zeros of. So it says finding all the real zeros. I imagine that means that either there's no imaginary solutions, or if there are, we don't need to list them. F of x equals, or also, real is a bigger umbrella. Rational and irrational are both underneath the real number umbrella. So maybe, because we say real, maybe we'll have irrational answers this time. But maybe we won't. Let's find out. It's a 4th degree. We will have 4 solutions or 4 zeros, including multiplicities. Like if one number worked more than once, it counts as a multiple solution. Let's list the possible rational zeros first. This is a good time for you to press pause and try to figure out the P over Q on your own based on what we talked about before. If you wait and do it with me, you're going to convince yourself that you got it and you understand. So I hope you hit and pause and try it by yourself. If you're ready to go over it, we should have, for P, the same numbers we had before. But for Q, since our leading coefficient is 10, I'll have to look at plus and minus 1, 2, 5, and 10. We're going to have a much longer list, although it is still finite. So what are the possible values for x if I list them all out? I'm going to put all these numbers over 1, then 2, then 5, then 10. If I have a repeat, I'm not going to write it. Plus, minus, and I'm going to be a little lazy, and I'm going to write plus minus one time in front, and I'm just going to rattle it off so I don't have to write it over and over, okay? 1, 2, 3, 4, 6, and 12 are all of the numbers I'll get over 1. Now, what about over 2? 1/2. 2 over 2 is 1. I don't need to write it. 3 over 2. 4 over 2 is 2. It's already there. 6 over 2 is 3. Already there. 12 over 2 is 6. It's already there. Moving on. Let's do everyone over 5. Nothing on top was divisible by 5, so these are all going to have to get done. 1/5, 2/5, 3/5, 4/5, 6/5, and 12/5. The 10 might give me some repeats from this list, so let's find out. 1/10. 2 over 10 is 1/5, already there. 3 over 10. 4 over 10 is 2/5, already there. 6 over 10 is 3/5, we already have it. And 12 over 10 is 6/5, already have it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, but I have both positive and negative. So I have 32 possible rational roots or zeros. So only 4 can work. It's possible that none of them work, to be honest, and we only have imaginary solutions, but we'll see in this example, we do have numbers that work. So now that we made our list of possible rational zeros, what do we do now? Normally we would just jump ahead and try synthetic division, but there's a lot of numbers on this list. So if I ever give you one for homework, I'm going to show you a cheap little trick for you to do when you do it on your own for homework if it's a big, gross problem like this one. What you would do is you would graph the polynomial maybe in your calculator or on Desmos and just do a little peek at the graph. You're going to look at your x-intercepts and use them to realize, well, I have 4 x-intercepts, so that means I have 4 real, not imaginary, solutions. They could be irrational though, but ballpark, this one, maybe this one's about negative 1.5? Negative 1.5? Question mark? What's that as a fraction? I'm glad you asked. It's negative 3 over 2. So perhaps I should start with that one. So how many real solutions do you see? 4. They all look pretty linear to me as well. We will do an example where I actually have the calculator underneath here because getting your window modified is a nightmare. Modifying to an appropriate window can be quite difficult. So when I do that video with the actual calculator, and if you have a calculator to follow along with, or if you can at least do it on Desmos, I'll do it on Desmos as well, I would definitely follow along, press pause, and actually try it. A lot of people think they get it, and then if I gave you like a calculator or Desmos type of pop quiz, people have a meltdown. So definitely follow along. Are there any imaginary solutions for this example? No. I see all 4 of my answers. If they were imaginary, I would be missing some x-intercepts, and we'll see that in a future example. So the graph is telling me to try negative 3 over 2. All right. So I chose negative 3 over 2. Even if you didn't have a graph, you would just choose from your list. I would usually start with 1 or negative 1. Now to do my synthetic division, I need to flip back to the problem. So I need 10, negative 3, and negative 29. 10, negative 3, and negative 29. 5, I just want to make sure I don't need a placeholder, and 12. And it looks like we're good in the placeholder department. We bring down that first number. I know this might scare some of you. We'll be okay. 10 times negative 3 over 2. 10 times negative 3 over 2, we can divide first. That's 5. And 5 times negative 3 is negative 15. 3 and negative 15 is negative 18. New coefficient times the divisor. So negative 18 times negative 3 over 2. Again, we could divide first. The 2 negatives become positive. 18 over 2 is 9. And 9 times 3 is 27. Negative 29 plus 27 is negative 2. Negative 3 over 2, press pause if you're confused or rewind please. Negative 3 over 2 times negative 2. The negative times the negative is positive. I can reduce those 2's first, think smarter, not harder, and we get 3. 5 and 3, adding straight down, we get 8. 8 times the negative 3 over 2. We'll get a negative answer. 8 and 2 reduce, we get 4. 4 and 3, negative 12. Negative 12, well that's wonderful, isn't it? And we get a remainder of 0. Now, this is going to be a third degree polynomial. 10x to the third minus 18x to the second minus 2x to the first plus 8. But I still can't factor this by grouping. So I'm going to have to keep doing it until I get it to work out. So I kind of pick another number. Maybe I pick 4/5. I think that was on my list. Something kind of close to 1. Let's look back. 4 over 5 is close to 1. That looks pretty good. I might try that one now. So let's just make sure we understand what we have here. X plus 3 over 2 and this whole factor multiply to give me my original problem. But if you pay attention, we can make our lives a little easier. A 2 can come out of everyone. Love that GCF rule, right? So if I divide by 2, I can multiply out front by 2. What do I end up getting? I'm just going to write the coefficients to save space, but I get a 5, negative 9, negative 1, and 4. That 2, I'm going to take that, I'm going to distribute that in here. Why do I like that? Well, look what happens. 2x plus 3, because the 2's reduce. That looks a lot more friendly than that mess over there. So now I have this, and I'm going to work on this. We said we were going to try 4/5. And if we get it down to a quadratic, either we'll factor that quadratic ourselves by hand or quadratic formula. Bringing down that first number, 5 times 4 over 5. Divide the 5's out, and we just get 4. Press pause if you're confused, and write it down. If you're in Algebra 2 Honors or higher, really these are things that you should be able to do in your head or with a little scrap work on the side. Negative 9 plus 4 is negative 5. Negative 5 times 4 over 5, 5's reduce, and negative 4. Negative 1 and negative 4 give me negative 5 again. All the 5's. So I'll get negative 4 again. Well, that works out beautifully. Remainder 0. So what else do we have? Well, I have the 2x plus 3. Now I have an x minus 4/5. That gave me 4/5 as an answer. And this scary thing, 5x squared minus 5x minus 5, close parentheses. I'm going to factor the 5 out of here and multiply it into there while I'm at it. 2x plus 3, 5x minus 4, well that's pretty cute. And then I have x squared minus x minus 1. We have a quadratic. Can you factor this quadratic with AC method and grouping? Chances are you probably cannot factor it with the AC method and grouping. What multiplies to give you negative 1 and then adds or subtracts to give you negative 1? Last time I checked, that wasn't so successful. So this is our equation that we're trying to solve and find the zeros of. So really the whole thing's equal to 0. Here we already got the negative 3 over 2 and the 4/5 from those. And I'm going to use the quadratic formula on that. If we use the quadratic formula on this, what do we get? X equals negative b is 1 plus minus the square root of b squared, negative 1 squared is 1 minus 4ac all over 2 times 1 is 2. Negative 1 squared is 1 minus negative becomes plus. 1 plus 4 is 5. 1 plus minus the square root of 5 all over 2. Now, these are irrational solutions. If I wanted to know the decimal equivalent of these solutions, we grab a calculator and we are going to type in a little bit there. So I'm just going to show you a bit. The square root of 5. Well, if I take the square root of 5, that's not what I wanted. Square root of 5 as a decimal is that. Right now it's positive, so I'm going to do plus 1 to add that 1 from the numerator. And I'm going to take that answer and divide by 2. Please do that in the calculator yourself and make sure one of the answers you get is approximately, that little squiggle, 1.6 for now. Now the other one, because there's 2 here, is also the minus. So again, I could take the square root of 5. Please don't go off of what you see me type and think that that means you'll do it correctly, because that's not always the case. I'm going to make this answer negative with the negative button. So I guess in this calculator I would have to type negative square root 5. Add the 1 because it's a positive 1. So you could also do 1 minus the square root of 5 and hit enter, whatever, you get the same answer. But hit enter, then divide by 2 after, and you get negative 0.6. Make sure you round correctly. So this over here and this over here, these are decimal approximations. And the only reason I did them is I want to compare it to the graph that I saw on the calculator before and think if they make sense. So about negative 0.5 and a positive 1.5. Looks like we got on our list right there from this list of answers. And then the other two were negative 3/2, which is a rational answer, and 4/5, which is rational. These are irrational. Flipping back to my graph, do these answers make sense? There's that one. That must be approximately negative 0.6. This one is 4/5, which we started with before, and that must be the approximately 1.6. So there we go. We got lucky right away. If we try something and it didn't work, so this is really 1 minus root 5/2, and this one is really 1 plus root 5/2. So if we tried a number and we didn't get a remainder of 0, we would just try another one. That's it, all it is. So really take a few minutes to really marinate and let this example sink in. And then we're going to, this one we'll do in a separate video, but I want you to try the following example on your own. Find all solutions. So I want you to apply what you just saw in the last 2 examples to this over here. You could call it homework, you could call it classwork. We'll see how this goes. Try your best. If you mess up, that's okay. And this will be continued in another video / in class. I hope you were able to get the examples written and are ready to ask lots of questions during class time. Have a great day.